In previous units, we defined the concept of integration and how we do it. So that was raising powers and reversing the process of differentiation. But we didn't really talk about what it could be used for and what it actually meant. So in this video, I'm going to introduce the idea of what's called definite integration for you. So that's integration where we introduce limits. So at this point, what we're going to have to do is make sure that when we do definite integration, there's one key thing we talked about when we did integration previously that we no longer use. And that's our constant of integration, the plus c. Because when we have limits, what we're going to do is eventually find a numerical answer for the problem. Now I'm going to tell you exactly what I mean, because the way I want you to think about it, I want you to think of definite integration as describing one set thing right now. I want you to think of it as finding a way to get the area underneath a curve. Now you could imagine I've given you a curve here. Let's call it y equals f of x. And I've got my y-axis going along here and I've got my x-axis going along there. Now imagine I rain off an area like this between A and B along the x-axis. And I say to you, right, what is the area of this section here underneath the curve? Well, you could imagine I do a rough sketch of that just now. That's what the area would look like in terms of just a general shape. It goes from A to B, job done. Now, finding the area of it, I could break it down into a nice simple shape. So I could break it down into a square and a little triangle and go for some composite shapes. The only issue is that the height of the function, so the height here, is given by whatever the f of x is. So I can't, it's not quite that simple. However, think to how we could also approach this. We could break this down into rectangles that go as high as the f of x, the further along we go. And what we'd be able to do with each of these rectangles is calculate the area, because we know how high up on the curve it would go, and then be able to add all the areas together. The only issue is, if you look at this, we're going to miss a section. It's not going to be accurate, because for this bit here, I'm going to miss this part there. This one going up to here, I've got a bit there I'll miss. This one going up to here, I've got a bit here I'll miss. This one here, I've got a bit there to miss. So I will miss some of the parts of the area. I'm not going to get an exact, definitive answer. Now that could be a frustration. When we calculate areas of shapes, we want accuracy. We want an exact answer. We want to know exactly how much it is. But to counteract that, we could always take each of these and split them in half. So if I split this one in half there, split this one in half there, these bits here will go up slightly higher. Same if I do it here. That bit will go up slightly higher. Same if I do it there. That bit will go up even higher. And I'll get some of the areas I've missed and take them into my calculation. So my inaccuracy, my error, will get less. If I then split these up again, it'll get even more accurate. I'm going to get more of the areas that I'm missing, more of the parts that are just cut out. Now, ideal scenario is I can split this area into an infinite number of these. So I could split this area into an infinite number of infinitely thin strips, which I could then calculate and add up. And that's where our integration comes into play. Because what we can do is then say that the area is equal to the integral of whatever the function f of x is with respect to x dx from x equals a to x equals b. So I can calculate it using the integral. I've got such small, minute parts that I've divided my section up into. This will give me an accurate answer. Now the key question at this point is, great, I'm telling you it's an integral with two limits, but how do I use the limits? What does that actually mean, and how does it come into play? Well, it comes into play in a fairly easy manner. We call it definite integration when we've got limits, because we're definitely going to get an answer. It's not going to give us anything generic. It's not going to give us a plus c with a function. It is going to give us a final, definite numerical answer. And the way to think of it is looking at this. So the integral from x equals a to x equals b of f of x dx, now this is just our generic function f of x, equals capital F of x here from a to b. Now capital F of x is the integral version of your function here. So whatever this is, x squared, x cubed, or anything even more complex, this, the big capital F of x, represents the integrated version of that. Once we've calculated the integrated version of that, that's when we can start to use these limits. That's when they can come into play. Once we've got the integrated version of our function, we substitute in the value at the top of the limit, we substitute in the value at the bottom limit, and we then find the difference. So this here just tells me I do the value of the integrated function at the upper limit minus the value of the integrated function at the lower limit. Once I've calculated that, that tells me the area underneath the curve. So that tells me the area in that space. So if I was to do it for that previous example, the diagram I showed you there, that would tell me the area of the part that I'd marked out in red. Now it is a lot simpler than it looks, and it's really simple when we get our head around the idea of what we're doing. So I'm going to show you a few examples of this just now. So I want to first calculate these two integrals. So the first one is the integral from 1 to 2 of x cubed dx. Second one, integral from 0 to 1 of 4x plus 5 dx. Now, the first thing you have to do in any of these sorts of questions is integrate whatever's in here with respect to the variable here. So this one is integrating x cubed with respect to dx. So it's going to be whatever we have here. So I've got x cubed, integrate that. Remember what we do is we raise the power and we divide by the new power. So I get x to the 4 over 4. Put that in your square brackets with the limits outside, because that tells you you're now about to take this integrated function between these two limits. Now, as I've mentioned before, note one key thing here. I haven't put a plus c. Plus c is when you get a generic function that falls into a family of functions where the value of that, when it varies, gives you a different function. Because we've got a specific function that's a definite integral, i.e. a definite value in area we're looking at, we don't include that plus c at this stage. We leave that out. What we now want to do is think back to what we said a minute ago. We then take the integrated version at the upper value and we subtract the integrated version at the lower value. So for this one here, that would be the x to the 4 over 4 at the upper value. So that would be 2 to the power of 4 divided by 4. Take away the integrated version here at the lower value. So that would be 1 to the power of 4 over 4. We then just have to calculate each of these. So 2 to the power of 4, well, that gives you 16. So 16 divided by 4 gives you 4. Take away, well, 1 to the power of 4 is 1, over 4 is a quarter. So it's 4, take away a quarter, which is 3 3/4 units squared. Now, because we don't know what units we're measuring in, we could just call it units squared there at the end. And that there tells you the area underneath that curve between these two values there. Even if we've got slightly more complex functions like this, 4x plus 5, we still do the exact same thing. So it wants the integral between 0 and 1 of this. So first thing we have to do is integrate the function. So we've got 4x, we raise the power, squared, and divide by the new power, plus 5. Now remember, if it's just a constant and we raise it, it just becomes x. We then put it in our integrated brackets and say the limit is between 0 and 1. Now at this stage, if you can simplify it, simplify it. So 4x squared over 2, I can simplify the constants for that, and I get 2x squared plus 5x between 0 and 1. So I've now got the integrated version and I now know my limits. This is when I substitute in. So I do the function at the upper limit, take away the function at the lower. So I get 2 times 1 squared plus 5 times 1, take away 2 times 0 squared plus 5 times 0. Well, 2 times 0 squared plus 5 times 0, that's nothing, so that whole bracket just goes, so it's whatever's left here. 1 squared is 1, so it's 2 times 1, which is 2, plus 5 times 1, 2 plus 5, 7 units squared. So that's the area for that curve in that section. Now, as I've said, even more complex functions can still have the same type of answer. The only thing you have to look out for is things like changes of variables or trig functions. They still get taken in the exact same way, and the exact same thing happens. So this first one here, integral from 0 to 1 of t to the power 4 minus 1 dt. Now remember, the key thing to look at is that. That tells you what variable you're integrating with respect to. So in this case, I'm integrating with respect to the t. So this function here, fully valid, and I could do every term going. So integrate t to the 4, so it's t to the power 5 over 5. Take away, well, integral of 1 with respect to t is quite simply t. And again, put it in the brackets to say we're going from 0 to 1 is our two limits. We then substitute top and bottom in and subtract to find the difference. So we do 1 to the power 5 over 5, take away 1, take away 0 to the power 5 over 5, take away 0. Now this is all going to become 0 again. Great, so we don't need to worry about doing this bracket. We then do this one here. So I've got 1 to the power 5, which is 1, 1/5. 1/5 take away 1 gives me negative 4/5. Well, hold on a minute. I can't have a negative area. Negative 4/5 can't give you an answer because it can't give you a negative area. But it can, because in this case, we ignore the negative sign. And we say, therefore, our area is 4/5 units squared. Now remember, we're not looking at the direction. We're just looking at the size of the area. Yes, it says negative 4/5, but all that means it's 4/5 units squared below the axis. So we ignore the sign and we take the mass of it. We take the size of it, or the magnitude of the number. This last one here, integral from 0 to pi by 2 of sine x dx. Again, integrating with respect to x. The only difference this time is it's a trig function. And we've done integrals of trig functions before, so we should know this. Integrate sine x gives you minus cos x. And again, we know that's going to go from 0 to pi over 2. So again, it's just a case of find it at the upper limit, find it at the lower limit, and find the difference. So I get negative cos of pi over 2, that's the upper limit, take away negative cos of 0. Well, cos of pi over 2, it's the equivalent of thinking of it as cos of 90, which we know is 0. So it's going to be 0, take away, well, cos of 0 is 1. So it's 0 minus 1 because of there, minus minus becomes a plus, so it's plus 1. Therefore, our area in this one is 1 unit squared. Quite a nice, easy one to finish with, but trig is the exact same. Anything where it's the area under a curve involving integration, it's the exact same set of steps. First you find the integral and you state the limits it's going to be between. You then find the number at the integral at the top limit and you take away the integral at the bottom limit when you've calculated it. Once you've found the difference between them, that is your area. And if, like this one here, you end up with a negative value, just remember that means it's pointing below the axis. So ignore the negative, take the magnitude, because that's still the size of the area you're looking at, which is the key thing we need to calculate.